All right, recording's rolling. So let's open with a demo.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of the 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. All right, as you can see, we got some nice standing plays, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there, see what happens. Let's start with a 449 hertz frequency.
So he said 449 hertz frequency, right? Right. Now, since you guys know the speed of sound is about what 300 something meters per second, right? About 340-ish, right? And he just said 449 hertz frequency. Could you guys calculate the wavelength from that? Right, you could, right? Oh, and you can see right here. You can see like a wave pattern. Now, just at a glance, without a whole lot of thought, it looks like a transverse wave type motion, right? But you guys know really where that's coming from, which is the air above it is compressing. There's like high and low pressure points. So the sound wave above it that's pushing the flames down, right? Or the opposite, right? Like vacuuming them up partially. That would be a longitudinal wave, right? Longitudinal, right? This point right here, is this point right here a high pressure or low pressure point? High pressure, because it's like pushing the flames down, right? What about this point right here? Low pressure, because like vacuuming the flames up, right? So we're getting oscillating high, low pressure, right? All right.
As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound.
Now, when he turns up the frequency, what's going to happen to the wavelength? Yeah, it's going to get shorter, right? Because wavelength and frequency wavelength have an inverse relationship. Does the speed of sound change when he's going to change the frequency? Speed's going to be the same, right? Speed of sound is whatever it is.
What happens here is more again now.
You guys hear a higher pitch, and yeah, you see like more humps there because the like a shorter wavelength.
See, each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck?
Hey, if you guys ever open a sound wave file, of course, it looks all like it's not like that sine wave that one says like a really flat like computer tone, like right? That's just probably something really close to like an actual sine curve, but of course you have actual music, it's a little bit more complicated. No, all right, my screen's frozen. All right, let's all right, axe that then. All right, let's bring that back over to all right, well, you guys have the idea. All right, yeah, that last one is kind of a clean sound, but also a song, so got kind of best of both worlds. All right, this thing is out. All right, let me recharge this. Okay, well, got a little demo up here for you guys, so that you guys can hear me now. All right, so today we're gonna do a speed of sound lab. You guys know there is a quiz tomorrow, right? Simple harmonic motion and waves. It'll be open notes. So you guys can use your chapter 14, 15 puzzles as part of your open notes. I'm going to pick those up tomorrow, so you guys can try them out with your quiz if you want to. Any notes you've taken otherwise, any of your labs, right? I was putting together this quiz, went through the labs you guys did, went through these problems, just anything that you guys have seen over the last couple of weeks, right? Can show up tomorrow on the quiz. Okay. So you guys good with what we're doing today, tomorrow? All right, so speed of sound lab. This is going to be really similar setup to number 71 from your textbook yesterday. You guys remember doing this? Okay. Now it's a little bit different because the textbook question, remember from yesterday, was if you know what the speed of sound is and you know something about wavelength that you can measure, can you figure out what's the frequency from the tuning fork? We're going to do sort of the opposite approach where I have a tuning fork, right?
And I'm gonna have you guys calculate what is the speed of sound. Of course, you guys kind of know what the answer is gonna be. Ideally, it should be about 340 so meters per second. Hopefully that's what you guys get. All right, so how are we gonna do this? All right. All right, so I've got PVC pipe. I've got a bunch of flasks of water. You guys know the PVC pipe is gonna be open at the top. All right, here's the pipe itself. All right, and then the water, the water level is going to effectively close the bottom end of the pipe. Right, there's gonna be a couple places where we strike this tuning fork. Guys here, where it'll resonate. So as you raise and lower the pipe in the water, you'd be like here. Well, first here, it'd be like, and then later on here. So let's find both those places because I got all the materials right here. Let's just flash them in front of the camera. Make sure you watch this video at home. Okay, got some water. You guys have classier glass looking bottles. Right, got a couple of PVC pipes. Okay. So let me get this water tank off here. So for the shorter length, you probably just need one PVC pipe for that. You can just lower it straight to the water. But for this longer length, you might need 2 PVC pipes. And for that, you can just attach them like this. You just hold them in place, right? And it's possible even for some of the lower frequencies that have the long wavelengths, even this might not be quite enough, right? Like this might be just like at the water level and then go 2 PVC pipes up and it's like, it would actually resonate kind of about here. So for that, to take care of that, okay, you guys see a little bit of advantage. The glass kind of has some of the setup already in place back there. Okay, what you can do is take a paper. This is like a card stock, so it has a bit more heft to it. Right, roll it into a cylinder. Right, throw this in here. Yeah, like that. And I have an even longer extension, right? So you guys could do this, right? If you had to. Okay, guys got that? Okay. Now for this 512 hertz. Oh, I forgot to mention that. Let me zoom in here. Okay. See, it has a number stamped on it. It says 512. It says C. Okay, guys, that's 512. What? What's the unit? Hertz. Yeah, 512 hertz. Right now, there are different standards for tuning forks and like scales, like musical scales. I went over 2 of them in class. I went like Pythagorean and equal tempered. I think it's I should look this up. I think it's called like scientific tuning or something. There's some like weird type scale they use for a tuning fork. So this might not exactly match that digital piano over there, like the 512 hertz, but right, so kind of close anyway. Right, but for this particular one, you probably don't need that cardstock extension on the pipes. You just use a pipe or 2. Okay. All right, so that's the materials in the setup. Right now, I'm going to demo one of these with you guys using this particular tuning fork to show you guys exactly how this works. Then I'll send you guys back to the lab area so you can pick out some more tuning forks. I've got a whole box of tuning forks back there. Well, several boxes actually, so you can just find the ones you need. All right, so first box says the frequency in hertz, and all you have to do is just copy paste this number straight from the tuning fork. So I would write 512 hertz straight from there. And if you strike this thing, pretty good. Length 1. Now, you guys got a diagram here, but this looks identical to what we did yesterday for number 71, right? Like these 2 pictures, right? And remember what we're working with. We're working with longitudinal waves, right? Which are pressure waves, which the technical way to draw is to just do a bunch of dots, like da 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 da. You guys remember there's like a high pressure point that develops at the closed end, like right above the water level, right? And possibly, to make this long enough, there might be another high pressure point that develops about 2/3 of the way up, right? Right there. Right. And then there's a low pressure point here and also a low pressure point near the top of the tube, but not exactly the top of the tube, but pretty close to it. Right. So you guys know that. But it's really hard to like sit here and do a bunch of dots and also interpret that. So it's really common to just whip off a transverse wave to represent that longitudinal wave. And that's what's in pink ink. You guys remember that from yesterday too, right? And so same thing here. What's drawn as a transverse wave is actually representative of a longitudinal wave. So what is this L1? Like the shortest length that it'll resonate. So I'm going to take these materials. I'm going to take it off screen if you watch this video. And I've got this water set up. And it's going to raise and lower it until you guys hear it resonate. Okay, so listen real close. You guys hear right there resonate? Right. So I take a meter stick, you can use a meter stick or a ruler. Okay, let's see exactly what distance that is. Right, so you guys see I'm going from the water level, right? From the water level? Am I going from the top of the beaker? No, going from the water level, because that's where it closes the pipe. Okay, and that is showing 16 centimeters. Now, 16 centimeters, right? You guys see I put meters? I'm trying to help you guys out by doing meters, because that's base SI units, gonna help you in calculations. 16 centimeters, how many meters is that? 0.16. So that's the number that goes here, right? 0.16 meters, right? Okay. All right, now what's the next place that's gonna resonate? You guys throw me a prediction. What's a good prediction for what this number should be? Look at this compared to this. Is that 2 times or 3 times the length?
0.48.
That 0.48. I like 0.48. Okay. This L2 should be approximately 3 times L1. Okay. Now it won't be exactly 3 times, but it should be approximately. So that's kind of the ballpark where you should be looking, and then you can raise and lower the pipes. Now for this one, I need to take 2 of these pipes and put them together. So let's put them together end to end like that, and just hold them together like that, because I need a little bit longer pipe. So throw this down here. All right, and here we go. Find L2. Right there. You guys hear it right here? Okay, it's resonating like loud as will be. Hold that. All right, and this is reading 50 centimeters. Looking at 50 centimeters. Hey, that is really close to 48 centimeters. All right, that's what we're looking for. It's about 50. All right, so back over here. I'm not gonna write 50. I'm gonna write what? There you go. 0.50. Yeah, so got. Okay. Right now, why is it not exactly 48 centimeter mark? Well, this wave, the 3/4 mark actually extends a little bit above the pipe, and same thing for the 1/4. It doesn't exactly align with the top of the tube, right? Which is gonna affect this procedure we're about to do. Okay? Because if you're looking for the wavelength of this wave, you might say, well, why didn't we just stop at L1 and just quadruple that, right? No, that should be approximately the answer, but not exactly the answer. Like quadruple 16 was that 64 centimeters, I think, right? Right. So that should be pretty close to the wavelength, but not exactly. So one procedure you can do with this lab, like alternate to what we're doing, it has to do with like the diameter of the tube. Like if you know the diameter of this tube, there's some little equation you can do to figure out like exactly how far above the tube it'll go. But we're not gonna do that. We're gonna do this method where we subtract the tube, right, and then go from there. And I think we did that yesterday too, right? Took the difference between that and got that. Right. So what is 50 centimeters minus 16 centimeters? Yeah, there you go. 34 centimeters or 0.34 meters. There you go. Boom. Right. All right. And you guys see right above the box, it tells you exactly what to do, right? Right. So pull this number off the fork, measure L1, measure L2, and then it tells, all right, so take the difference. Okay. Now, guys, that difference represents how much of a wavelength? Half a wavelength, right? Isn't this half of the wavelength? Like half of the S curve? Right? Right. So to get the full wavelength, what's the full wavelength of this one? 0.68 meters, right? That's true. You just have to double it. And that's exactly what it says right above the box, says double that difference, right? There we go. Right. So now we're getting really close, because the point of the lab, like your goal is to figure out, can you figure out the speed of sound? Right, we're going to calculate that, right? And one step to go. Speed of a wave is equal to wavelength times frequency. Right? Really important wave equation, right? Meters per second, meters per second. Right? And we have both these guys. We said this guy here is 0.68 meters. We said this guy right here is 512 hertz straight off the tuning fork. Hertz is the same thing as 1/seconds, meters per second. Right? Put it all together. Oh yeah, we're looking for what number again? Hopefully,
340.
yeah, about 340-ish meters per second. Let's see how close. 348 and change. Yeah, and that'd be meters per second, wouldn't it? Yeah, that is extremely close to the textbook value of what we're looking for. Right? Even the speed of sound really depends on the temperature of the room too, and all that stuff. So okay, it's probably a tiny bit too big, but that's fine. That's a really good result. Okay, it's extremely close. So that's the last box right here. 348 meters per second. All right, all right. All right, so back in the lab area, you guys have well, all the materials to do what we just did, right? And you guys see on the back, can you guys find a couple of new tuning forks with different frequencies, right? And then do this with your lab partners and turn this into the gray tray by the end of class, right? Right. If you have a few spare minutes, then you can study for a quiz tomorrow, right? So if you need any help, let me know. Walk back there and help you.